Hello everyone. In this presentation I talk about knowledge graphs and how they can be used to create digital twins for AI in a production context. What we would like to do here is create AI models that are able to improve our production process. For example, reduce the scrap rate, reduce the production time, or improve the product quality. Typically, one would collect a whole lot of measurement data and then perform a learning step to create this AI model. However, in a production context, there are a number of problems associated with this typical AI approach. For one, some of the production parameters that are relevant for the AI model might not be directly measurable or might be too expensive to measure. Next, the measurement data volumes might be too low, which is, for example, often the case in a high-mix, low-volume production context. Typically, also a lot of the production knowledge that's available within the company might be excluded. Think, for example, of expert experience. Finally, this approach typically leads to a black box type AI model, which is not explainable. Our goal here is to facilitate the creation of an AI model that not only includes measurement data, but also a variety of other heterogeneous data sources that can be found in a production context, such as log files, simulation and other types of models, information from the MES and ERP system, tech domain knowledge, and user manuals. Typically, these different data sources are also found in different physical locations within the company, such as on time series databases or SQL databases, within code, access through REST APIs, within PDF files, and so on. Our idea here is to use a knowledge graph at the center of the data architecture, which is able to capture all of the relevant concepts and the relation between those concepts contained in these different heterogeneous data sources that are typically found in a production context. This knowledge graph should facilitate a connection between these different heterogeneous sources and create a common vocabulary among all of the concepts, facilitate knowledge and search, capture, and creation, and crucially here, connect these different heterogeneous data sources to facilitate data search. This leads us to pose the following data architecture. On the left-hand side, you can see the operational zone with the different devices on the production floor creating data, and on the right-hand side, different applications using this data. Specifically for our context, creating and training AI models is the application of interest. In the middle, you can see the digital twin with on the top an offline zone which gathers data from the operational zone and combines it with other data sources within the company. And on the bottom hand side, the online zone which contains applications such as dashboarding and streaming analytics. In the center of all this is the knowledge graph, which is connected to the different parts of the data architecture. Typically, measurement data is gathered from the operational zone combined with other information within the company, and all of this is referenced within the knowledge graph in the center. Next, the data scientist can use the knowledge graph in order to query all of this data and train the AI model. Finally, users of the AI model can also reference the knowledge graph when deploying the AI model in online applications. As an example, consider the milling of a compressor housing on a CNC machine with a specific sub-step of milling a rotor bore. For this, we use a certain milling bit, and in the end, the bore diameter is being measured. The data scientist might be asked to create an AI model which is able to predict whether or not the diameter of the bore will be within tolerance. In order to do so, we will go through a number of steps, such as identifying and analyzing what the diameter is correlated with, creating a model for this correlation and training it on a data set, deploying this model so that it can be executed and in time can also be validated based on new data. In order to do so, in our case, the data scientist will ask the production expert to create that part of the knowledge graph which is relevant to this process. So this will contain concepts such as a compressor housing, a CNC machine, a milling bit related to their appropriate properties, such as material hardness of the compressor housing, bed temperature of the CNC machine, remaining useful life of the milling bit, and so on. Crucially here, data on the different concepts in a knowledge graph are typically found in different locations throughout the company. For example, which compressor housing is milled on which CNC machine can be found in the MES system. Material hardness might be found in a PDF document, and time series data such as bed temperature and spindle torque can be found in time series databases. As a first step, the data scientist will find out what the bore diameter is correlated to. In order to do so, he could talk to an experienced operator, which might express a suspicion that the bore diameter is correlated, for example, to the bed temperature and the remaining useful life. Crucially here, the data scientist will add this knowledge as a suspected correlation between the parameters to the knowledge graph. Next, the data scientist can reference the knowledge graph in order to find the correct data, for example here for the bore diameter and bed temperature, which allows him to plot and analyze whether or not these parameters will indeed be correlated. Next, the data scientist creates a correlation model, which models our suspected correlation, and adds this model again to the knowledge graph. The knowledge graph can once more be referenced in order to find the correct data to train the AI model. If it is found that the AI model is not accurate enough, the data scientist can also use the knowledge graph to find out how additional data can be created. Information on the deployment of the model is then also added to the knowledge graph. This will reference the data architecture shown earlier. Finally, in order to execute the model, additional data such as which input and output are related to the model is added. Later on, other stakeholders can also reference the knowledge graph in order to find information on the bore diameter and information on how to execute the correlation model in order to compare and validate the model. Finally, I want to show a short example of how the knowledge graph can be connected to different data sources. In order to do so, we created a small example using OnTop, where OnTop allows to create a mapping between the knowledge graph and a SQL database, which in turn allows the data scientist to pose Sparkle queries over the knowledge graph using the concepts of the knowledge graph, such as, in this case, compressor housing, CNC machine, milling bit, and so on. The Sparkle query is then translated into a SQL query, which allows to retrieve the data from the SQL database to the data scientist. So, in conclusion, we saw a knowledge graph-centered data architecture, which should allow to create AI models using a wide variety of heterogeneous data sources, as can be found in a production context. Further activities include being able to properly express different types of knowledge, such as the operator experience, which we saw in the example. Furthermore, we want to create a software stack which is able to query a large variety of data sources, where we just saw the example of how to query SQL databases using OnTop. And finally, we want to validate all this on an industrial scale example. Thank you for your attention.